Okay, welcome to our first lecture for the 2025 AEMT program. Glad to have everybody here. We're going to get into this first lecture. We're basically going to talk about the cell, and we're going to kind of look at that. And it's kind of strange how it works with whether it be an EMT class, AEMT class, or even a paramedic class, that we start off talking about the cell. And I think it's important to understand why. The why is that it's the job of any pre-hospital care professional, should be the job of any practitioner, is to stop cellular death, right? That should be our first and primary goal, is to stop cellular death. But also, as an advanced EMT, your scope of practice is going to change quite a bit, and you're going to affect the cell even more. But you're going to be administering IV fluids. IV fluids is going to affect cells. We're going to talk about that. And so let's dive into the cellular anatomy and some of the cellular physiology parts of this lecture. So what is a cell? Well, the cell is composed of chemicals, and they're surrounded by a chemical environment. When we look at chemistry, it's a study of composition of substances and interactions between various elements and compounds. Chemistry, it's going to allow the cell to engage in metabolism and maintain something of homeostasis. I'm just still kind of working out the bugs on this program. I'm sorry. Just a second. Hope everybody's doing good today or tonight, whenever you're deciding to watch this lecture. When we talk about a chemical element, so a chemical element is an element, it can't be broken down any further. When we're talking about elements, if you remember back in school talking about the periodic table, those are elements there, and they can't be broken down any further. An atom is the simplest unit of an element, right? And it's going to consist of three types of subatomic particles. You're going to have your neutron, and a neutron kind of goes, meaning it's electrically neutral. It doesn't carry a positive or negative charge. Then you have the electrons, and electrons are negatively charged particle. Then you have protons. Protons are a positively charged particle. So electrical charge of subatomic particles allows atoms to bind with atoms of opposing charges. So meaning, if you have a positive and a negative, well, they will attract each other. Some of you guys have significant others out there that you're with right now because you guys are complete opposites. Sometimes opposites attract. Usually, if the same element carries the same charge, so if you have two positive charged elements, then those are called cations. If those cations are the same, they'll normally repel one another. They won't attract one another. And that's the same thing for a negatively charged anion. They normally will push each other away. They will not attract one another. And this is important because the body uses chemistry to produce certain reactions that we're going to get into. So we just defined an ion, and we called that the ion's the smallest part of the atom. We talked about the cation being a positively charged particle and an anion being a negatively charged particle. And then we have electrolytes. Electrolyte I think that's coming up. But electrolytes is when you take something like sodium chloride and you drop that into a solution. And I'm going to have to pause you here for a second because I need to get my whiteboard out so I can draw this and explain to you what an electrolyte is. So hang on one sec. All right, we're back. All right, so let's draw this out. It's easy. It's not. This part's really not hard to understand, but they just don't have a good slide on it. Okay. This is not. Oh, it's not. Oh, hang on a second. It's not the best. Not the best whiteboard. I'm not. You know, my pen is not really calibrated for this yet. But hang on. Let me get this drawn out. Oh, it's crazy. That's crazy. Well, hang on. Sorry about that. Oh my God, this hurts. This painstaking right here. All right, sodium, and we have chloride. Right, and normally it's sodium chloride, table salt, right? And so if you had NaCl together, right, and you decide to drop it in some water. Okay, so you're going to drop it in some water, which is H2O. You have your sodium, and which is your cation, and your chlorine, which is your anion. And guess what they're going to do? They're going to disassociate in this water, right? And when they dissociate into negative and positive ions when placed in water, that is an electrolyte, right? That's what it is. So you have NaCl, and that's all the electrolyte is. Electrolyte is a substance, chemical compound that dissociates into negative and positive ions when placed in water. All of that for that, right? Okay. And so here's a typical structure of an atom, right? So you see that you have your neutrons here that do not carry a charge. You have your protons right here that are electrically charged, positively charged rather. And then you have your anions, or your electrons that are negative, have negative charges. The electrons like to hang out here in these called shelves. That's where they like to hang out at. And different elements have different numbers of electrons. And so here's another shelf over here. So you have different number. This happens to be a carbon atom. This is a neon atom. So again, electrolytes are compounds made of a positively charged ion, a cation, and a negatively charged ion known as an anion. When electrolyte is placed in a solution, just like I drew out a second ago, it will dissolve into charged ions. And they do this because the electrons are kind of move back and forth. And that's how that works. It's kind of really this is not going to be a chemistry class, but what's important, I guess, is to understand that, and I'm going to do a different PowerPoint here in a minute that can kind of make this a lot simpler for everybody to understand of why it's important to understand the chemical structure. So you have 4 elements that comprise most of the body's atoms. You have hydrogen, oxygen, carbon, and nitrogen. And if you look here, you'll see what their function and role is. And so if you look at oxygen, a compound of water and other compounds, oxygen's a gas, and we already know it's essential for respirations. But what about like calcium? Calcium is found in bones and teeth. Everybody probably knew that already. But the function here that it has with nerve impulses and muscle contractions and clotting. So a lot of times people think it's potassium that does that. Like some people, when you have leg cramps, you're thinking, oh my God, it's because I don't have enough potassium. Well, potassium, if you come down here, has nerve impulses and muscle contractions too. But sometimes you can have, You can have more of a, what I'm saying is you could have muscle contractions too, and cramps when calcium's low. So it's not always the potassium's not always the number one thing there. So it's something to think about. Remember that about calcium. Calcium is the principal cation that causes skeletal muscles to contract. And that's what I was trying to think of a second ago. So remember that might be important for later. All right, so we look over here. We're talking about water. If we look at water, and when we talk about the body, 60% by weight. It's contained in 2 major compartments. You have intracellular fluid and extracellular fluid. If you look over here, when we talk about intracellular fluid, we're talking about water within the cell. And that's about 75% of the water that's used in the body is water within the cell. It's pretty interesting, right? Then you have the extracellular fluid. And this is fluid that's found outside of the cell. And it's going to include intravascular fluid, so blood flowing through your veins. And it's also going to include interstitial fluid. And this is fluid found out around the tissues. It's important to understand that because we're going to be given IV fluids. And when you're administering normal saline, you need to know exactly, why am I administering it, right? Because I need to either be replacing intracellular fluid or extracellular fluid. And most of the time, we're looking to replace that extracellular fluid inside the intravascular space. That's usually the goal that we have when administering IV fluids. Some terminology that's important to understand here, and it can be confusing, but we're going to kind of go through it. First things we're defining here is solutes and osmosis. Right, and so solutes are foreign particles in body fluids. It's not the fluid, it's the foreign particles in the fluid. And so these foreign particles can be electrolytes, like we just showed, sodium chloride. Could be carbohydrates, proteins, lipids, and even drugs. So those are solutes. Understand that H2O or water, right, is the solvent. So don't confuse those. Don't confuse solvent with solutes. The other thing we need to talk about is osmosis. So osmosis is a type of diffusion that involves the movement of water molecules across a semi-permeable membrane, right? Movement of water across a semi-permeable membrane. This talks about along a gradient from lower to higher solute concentrations. But that should sound familiar back from EMT school, because we talked about something called diffusion. And diffusion shares a very similar definition, right? So when we talk about diffusion, that's the movement of particles from an area of higher concentration to an area of lower concentration. Usually, we'll choose to use the word osmosis when we're talking about water particles or water solutes that's moved by water. Let me rephrase that. Solutes that's moved by water, and also usually we're talking about a semi-permeable membrane there too. So diffusion, we normally like to relate that to gases. And, when we're talking about carbon dioxide and oxygen and how they diffuse along the alveoli, that's usually the word we like to pick for that is diffusion. But osmosis when we're talking about water solutes. Osmosis is the process of water equalizing concentrations of solutes across a semi-permeable membrane. Again, the movement of oxygen and carbon dioxide between alveoli and the bloodstream, that's going to be called diffusion. So we have osmotic pressure, and osmotic pressure is going to be caused by the differences in the concentrations of the solutes. Okay, caused by the different concentrations in the solutes. So if something's more concentrated, it's going to want to diffuse from the most concentrated side to the less concentrated side in order to become equal. And it's those differences in the amount of solutes that causes that pull of the water across the cell membrane. It's measured in millimoles. Not really important there. Alcotic pressure is a portion of the total osmotic pressure. And this actually returns fluid to the bloodstream. We'll talk more about that in a second. So now we need to define some terms. We have isotonic, hypertonic, and hypotonic. Let's see here. So I want everybody to understand that last slide, though. I want everybody to kind of get the idea behind that, and I may actually draw that out. Hang on a sec. Okay, we're back. So let's try to struggle through the board here again to draw this out so everybody understands. It's not too hard to understand, but I want to make sure everybody does. Oh, sorry. Hang on one second. It disappeared. There we go. All right. So again, it's caused by those difference in concentrations in solutes. So let's say I have some sodium. Let's actually draw it out. Let's say I have some sodium here. So I have 4 molecules of sodium. And remember, you're going to have that membrane, right? That's the membrane. And we'll talk more about that, but the function of the membrane is to keep stuff in the cell that's supposed to stay there. And keep out the stuff that's not supposed to be there. All right, so boom. All right, so we had 4 molecules of sodium inside the cell, right? And we have 2 molecules of sodium outside the cell. So what's going to happen is this is more concentrated, and it's going to actually draw this sodium out of the cell to equalize that, right? And that's a pressure that's caused by that being unequal. That's osmotic pressure. Now, you have something called oncotic pressure, right? And oncotic pressure is a portion of the total osmotic pressure, but in oncotic pressure, it's actually going to return fluid back to the cell. All right, that's oncotic. All right, so oncotic pressure is kind of ruled by something called albumin. Albumin. It's found in the blood plasma. It's a particle in the blood plasma, or I shouldn't say particle. Let's say it's just in the blood plasma, and that's what's going to draw things back into the cell. So it kind of reverses oncotic pressure. Okay, so that is what when we talk about oncotic pressure. That's what we're talking about. All right, so let's talk about this. Go back to the definitions of isotonic, hypertonic, and hypotonic. And so when we're looking at that, let's look at isotonic first. So if we're looking at something called normal saline, 0.9%, that is going to be something considered to be isotonic. It doesn't draw fluid from the cell, and it doesn't push fluid into the cell. Hypertonic is a more concentrated solution, so it has a higher osmotic pressure, right? And we just mentioned that, how if something is more concentrated, then it's going to draw fluid away from that. And that's just the example I just finished, that I just showed right here. So this would actually be considered hypertonic if this was this is excuse me, extracellular fluid, intracellular fluid. It's going to draw sodium out to the extracellular fluid. And so that is going to make this hypertonic. It's going to make the cell hypertonic. So at the end of the day, once this is complete, the cell is going to be much smaller than it was before because it's drawing fluid away. It's drawing the sodium away, and fluid follows sodium. So that's where it's going to happen. Water follows sodium, rather, and the cell is going to be much smaller. Hypotonic is the opposite of that. It's less concentrated solution. So if you had like a 0.45% normal saline, right, instead of 0.9, we're talking 0.45, that's less than 0.9. So it's a lower concentration. So that's going to cause water to actually leave the bloodstream and enter the cell. So that's going to be the exact opposite of hypertonic. And so that's what this slide shows. Here we have hypertonic, isotonic, and hypotonic. See here, isotonic, there's no net osmosis. Here's the intracellular fluid. Here's the interstitial fluid. It's not drawing anything out. Hypertonic is going to draw fluid out of the cell into the interstitial fluids. And hypotonic is going to drive fluid into the cell. And so there's a better slide coming up that kind of shows that. Here's a cell. It's isotonic. It's not drawing water in or out. Hypotonic. See how your cells get, it's swelling. And the first one I drew on the board was hypertonic. And see how much smaller this cell is compared to this, and even compared to that. But it actually draws away. That's important to understand. So if I said solution A has a higher concentration than solution B, which term properly refers to solution A when compared to solution B? Let me read it again. Solution A is a higher concentration, right, than solution B. Now the question wants you to properly refer to solution A. Which term would properly refer to solution A? And so that would definitely be hypertonic. Would definitely be hypertonic because it's solution A has a higher concentration, and it's going to give up that concentration to make that equalized. The good old sodium potassium pump. So the sodium potassium pump, it's a protein found on the cell membrane, and it keeps the ions at a proper level inside and outside the cell. We're going to talk about that more in a slide in just a few minutes, but we're going to go into that I won't say much more detail, but hopefully better to be able to understand it. Potassium is your notified by your K positive here. And you have sodium is a positive ion as well. And so think about it. We need sodium to go inside the cell to make the action potential of the cell happen. And just from what I showed a minute ago, these guys want to, through osmosis, they want to be equal. Well, if sodium gets inside that cell, once it goes inside, guess what? It wants to equalize. It wants to bring in its buddies inside that cell to make the outside equal with the inside. Well, if we allowed that to happen, there would be too much sodium water follows sodium. And so what would end up happening is it would be calling upon water, hey, come on in the cell, and that cell would become too large, and it would actually lysis or burst. And so we don't need that. So this process actually pumps out sodium against its will. It's like, nope, you're going out. You're leaving once everything happens that we need to happen inside the cell, it's going to pump it out. And that's why the sodium potassium pump is so important. However, it takes energy to work because it's actually pumping that sodium out against a gradient. And so it takes work. So if there's not enough energy produced through aerobic metabolism and sodium's not removed from the cell, water will enter the cell in quantity such that the cell will burst and die. That's what I just talked about. There's two types of transport when we're talking about cellular transport that you need to be aware of. One is called active transport, and the other is called passive transport. Active transport requires energy, and it's responsible for the potassium being able to enter the cardiac cells. That's why active transport is so important. Passive transport, however, it requires no energy. So make sure you understand that and that you know that. So again, the sodium potassium pump here on the cell uses energy to move sodium and potassium ions across the membrane. And that's exactly what it's doing. ATP is the energy provided to that sodium potassium pump to do its job. Okay. Well, and we'll talk more about that later too. So when we look at the energy of the body, we talk about metabolism, again, aerobic and anaerobic. Remember, aerobic is with oxygen, anaerobic is without. Energy production in cells is a chemical process of breaking down glucose. Cells require a constant supply of glucose and oxygen for their survival. That glucose comes from the digestive tract and oxygen from the respiratory tract. When we talk about metabolism, there's a couple of new terms that you may not be familiar with. We have anabolism and catabolism. I'll get it out in a second. So anabolism is to synthesize more complex substances and require energy. So an example of that would be the breakdown of glucose into water, carbon dioxide, and energy. That would be an example of catabolism. Anabolism, I think I may have screwed you up on that. Let me start over real quick. Anabolism is to synthesize more complex substances that require energy. Catabolism, you're going to break down complex substances into simpler ones. And the example of that is the breakdown of glucose into water, carbon dioxide, and energy when we do aerobic metabolism. That's an example of catabolism. Hope I didn't screw you up on that. This is talking about something known as the Krebs cycle. I don't think we have to get that crazy with this. As long as you understand when we talk about aerobic and anaerobic metabolism, the first phase of that process, remember you have oxygen comes into the cell and finds glucose, and then that glucose is broken down into pyruvic acid. That part by itself, right, could be anaerobic, meaning if it's still going to make pyruvic acid if oxygen's not there or glucose is not there. All right, so that's anaerobic. And then the second phase here, aerobic metabolism, basically what you need to know is we're going to get a lot of ATP and a lot of heat. We're going to use that heat to warm the body, right? We're going to use the ATP to run the sodium potassium pump and all the other functions of the cell. And of course, if oxygen levels aren't restored quickly, cellular death will occur. That's why it's so important for us to stop cellular death before we get to tissue death. Let's talk a little bit about this. I'm going to talk about it more in later slides, but it's important. Let's get the terminology out there and let's start understanding this. So when we talk about acid base balance, right, what we're talking about is we're going to be looking at the pH. And that pH is a potential of hydrogen. So anytime you see hydrogen, you need to think of an acid, right? Because hydrogen is either going to make an acid or it's going to make a base, depending on the number of hydrogen that you have. So acid here is a substance that can donate a hydrogen. And we'll talk about how that donation process works. Alkali is a substance that has enough in it to where it could accept a hydrogen. We're talking about a hydrogen ion here. Acid-base balance uses a measure called the pH scale. And the pH scale is an inverse logarithmic, and it ranges from 0 to 14, with 7 being neutral. So 7 is neutral. Anything less than 7, you're dealing with an acid. Anything above 7, you're dealing with a base. And it's important to start soaking this in, because understanding acid base is it's the bread and butter of an AEMT. Acid-base balance. So an acid is a concentration of hydrogen ions. So if you have a lot of hydrogen ions, you're going to have some acid. Now, an alkalotic is a concentration of hydrogen ions that are low. So you've got about hydrogen by itself. A buffer system is when excess hydrogen ions are converted into a substance that prevents acid accumulation, making acid-base balance. So I have a different slide that we're going to walk through, and I can make this, I think I can make everybody get this. You just have to kind of go slow with it, but I think I can help you guys. But those are some of the terminology I want you guys to start soaking it in. We have to talk about the membrane potential. And the membrane potential, at the end of the day, y'all, the membrane potential is talking about the electrical impulse a cell's going to have. Cardiac cells, right, produce automaticity, right? And so they can fire by themselves. That's what we're talking about. We're talking about the heartbeat. We're talking about when a brain cell fires and you understand something, that moment the light bulb goes off. And that's what we're talking about here. We're going to talk about these polarized and depolarized and what that means. In this book, I think it says cell polarization when there's a difference in electrical charges across the membrane. And it talks about depolarization as being when the imbalance reaches a certain point, electrons begin to move across the cell membrane to equalize the charge, and that stimulates adjacent cells. Then you have repolarization, and that occurs as the difference in charges is restored. So I'm going to show another video here shortly to explain that. All right. Here it is. It's the cell. This is kind of the difference in AEMT versus EMT. A lot of the anatomy and physiology we're going to cover, you've already had. But there's some things here about the cell, its cellular anatomy and physiology that you need to understand. So we have a cell coat, a cell membrane, we have a Golgi body, we have the rough endoplasmic reticulum right here. This is the smooth endoplasmic reticulum there. On top of those should be some tiny little ribosomes. There they are. They're right over here on the rough endoplasmic reticulum. They have these things called ribosomes. Lysosomes right here. Free ribosomes run between the rough endoplasmic reticulum and the smooth. And you can read about these here. I want you to look at this. I want you to understand it, of course. But when we look here, this is going to lay out the functions of the cell, of these special components of the cell. I want to point out a couple that you need to know. And let's go back and look at the smooth endoplasmic reticulum right here. See that right there? All right, so steroid metabolism and drug detox occurs inside the smooth endoplasmic reticulum. And remember the lysosomes right there? You're looking at the lysosomes, digestive enzymes that protect against disease, and they produce nutrients. I like lysosomes because if this was a lymphocyte, which is a white blood cell, and it was out doing patrol and it found a invader, what it does is it actually sucks that invader into the cell, so it eats it. And once it gets inside the cell, lysosomes just attack it, and they actually remove the danger of the bacteria. And then, just FYI, they'll put pieces of that on top of the cell, and a killer T cell will come by, pick it up, and that's how you start building immunity to things. It's pretty interesting. So remember that about steroid metabolism and drug detox, and remember about lysosomes and what they do. All right. Cell membrane, we talked about this semi-permeable, allowing water and small molecules to move through it. So it's going to allow your sodium to kind of come in. It's going to allow your water to come in, or your extracellular fluid come into your intracellular fluid, right? It's going to allow for that to happen. The wall of the cell membrane is composed of this called phospholipids. You have channels. These channels, like the sodium-potassium pump, allow certain substances to move through at certain times. Movements of other substances are regulated by electrical charges of molecules that comprise it. The cytoplasm, that's the fluid medium within the cell. So inside that cell, the intracellular fluid is known as cytoplasm. It has a nucleus, and the nucleus is where DNA is comprised of, and your chromosomes, your body's genetic code, all of that is located inside the nucleus. That is where DNA transcription happens between there and the ribonucleic acid, all of that, the RNA, all of that happens inside the nucleus. It's transcribed by those ribosomes into the proteins. So that's pretty neat how it works. The Golgi apparatus modifies proteins. The mitochondria, the powerhouse of the cell, and it's called that because it produces energy in the form of ATP through oxidative phosphophosphorylation. All that is the Krebs cycle, but I don't think you really need to understand the Krebs cycle here. Just need to understand about aerobic and anaerobic. The vacuoles store and transport proteins within the cell. The centrioles, they provide support, form microtubules and spindles. And this is how things move around inside the cell, is on these microtubules. We talked about the lysosomes and what they do already. You need to know this. The 4 types of tissue of the human body. It's epithelial, connective, muscle, and nervous. So you need to know those. All right, guys, hang on 1 second. I'm going to pause you, and we're going to talk some more about the cell. Hold on 1 second. Okay, y'all. So I want to look at now, again, we're going to talk some more about the cell, right? I want to try to make this a little bit easier to kind of grasp. And so if I ask you, what do you think, or what is the general function of a human cell? Think about that. What do you think the function of the cell is? Well, the answer to that is to provide a specific purpose, a specific function within your patient's body. That's what the one human cell does. And I think a long time ago, when I was just a child in school, I used to think that cells were all the same. And they're a lot of their anatomy is the same, but their functions are so different. And so then the next question would be, well, what is the general function of a cell membrane? Right? We just talked about the cell membrane a little bit a minute ago. But the general function is to keep the stuff that's supposed to be inside the cell, and to keep the stuff that's supposed to be outside the cell. And that's what its job is. Its job might be hard, but it's not real hard to understand. So what is homeostasis? Well, homeostasis is the tendency toward a relative stable equilibrium between interdependent elements, especially as maintained by the physiological process. But it's to maintain that a state of controlled chaos. And I always compare it to the thermostat at home. If 72 degrees is where you like to be comfortable at, so that's where we want it at. And so if it's cold outside, the heat's going to kick on, and it's going to hit 72, and guess what? That's going to turn off. And that's what the body tries to do. It tries to keep us at our peak state so that we can function. Well, in order to try to bring this thing out, I wanted to try to, I don't know, dumb it down a little bit, because even I, as a teaching this stuff, if I have to read about it every time I teach it, it's not easy. The definitions, the terminology, it's not always, they don't make it always easy to understand what's going on inside a cell. And so what we're going to do is we're going to compare this to a schoolhouse and to school, basically. And we're going to see how that works out and see if everybody understands it a little bit better. So when cells are born, they grow up and they go to elementary school, they go to middle school, they go to high school. But at some point in time, they're going to specialize and they're going to go to college. And some of these cells go to the School of Cardiac Function. Some of them go to the School of Muscle Movement and Coordination. Some of them specialize in brain function. And there's other schools out there too. There's the School of Liver Function, School of Pancreatic Function. So any organ system we have, there's cells. And they have special things that they do. A cardiac cell does something special that a brain cell doesn't do. And a brain cell does something special that a cardiac cell doesn't do. So they become specialized. And the body's no different than this. They're gonna specialize these cells. So the schoolhouse theory. So if you were to ask teachers of these schools, where is the most purposeful, thank you, learning occurring at the school? And what they're asking is, do you think these kids are going to get a better influence inside the classroom or outside the classroom? I've taught this before, and it's amazing to me that most of us always say outside the classroom. I think it's because we have type A personalities. We like being outdoors. We like putting our hands on things. We feel like that's where the most learning occurs. But for my skit to work, the answer is going to be inside the classroom. Most learning is going to occur inside the classroom. And the reason why that is because for the cell to function properly, everything, it needs to happen inside the cell. So the greatest influence over students occurs inside the classroom. I gave it away already. For a cell to propagate its function, it must happen inside the cell. So for whatever function of this cell is, whether it's a brain cell or cardiac cell, for everything to function, it has to happen inside the cell. All right. So the primary students who attend school, who are going to be our students. And so here we have sodium. We have sodium here is going to be one of our students. I want to introduce you to the next one. Potassium is going to be our second student. And calcium will be our third student. Now, all three of these students have different personalities that we're going to talk about. So sodium, when we talk about sodium, sodium is the action guy. Sodium, wherever sodium's at, that's where the action's going to be. Remember, though, it's inside the cell that propagates an action. So sodium needs to be able to move in to add its positivity. But sodium is like the senior of the high school. These are the guys that are on the football team. All right, these are the guys that are the most popular around. Everybody wants to be around sodium. Sodium is where the party is. Let me introduce you to our next student, which is going to be potassium. And potassium potassium, it loves being inside the cell. It loves the predictability. It loves the control of being indoors. Sodium, when compared to potassium, both are positively charged anions. However, sodium tends to be more of an optimistic consistently than potassium. So potassium is a little slower to pull the trigger. They want to think about things a little bit more. And that's kind of how they want to work. So potassium is the pessimist. Even though it's a positive charge ion, it tends to see the world from a glass half empty perspective. And they prefer to spend the day inside of the building. These are your introverts. All right, hope you're all with me now. Stay with me on this. Third student is going to be calcium. And I want you to think of calcium as the freshman of the high school. They feel awkward. Probably the best way for them to fit in is to hang out with the popular kids. So they go over to sodium and say, can we hang out? And sodium said, get away from me. I don't want you near me. And calcium's they're very persistent and pleads with sodium. And sodium remembers one thing. They hate to open doors. Sodium is known just to go and stand there and look at the door and never even open it. So sodium reconsiders and says, okay, calcium, look, I'll make you a deal. If you want to hang out with us, you can, but you always have to open all the doors. And Calcium, they love that idea. Calcium says, great, we'll do that. So, at the beginning of the school day, we have potassium on the inside doing their thing on the inside. We have sodium out here playing, hanging out, partying, and calcium hanging out with sodium. So this is how the day starts right here. So this is the resting potential. Okay, so this is where the cell's at rest. There's no action happening. Everybody's reset, and the cell, whatever its function is, it's not doing it, because this is the resting potential. And this is homeostasis. The body works very hard to reach this potential. But what would a school be without a PTA? A bunch of crazy ass parents who are concerned about sodium, that they're spending too much time on the outside. And then you got parents of potassium, they're calling raising hell. They're concerned about the time that's spent inside. And so all these parents decide to call the Board of Education, and they demand that they hire a school bus driver. All right, so government worker. The school bus driver is a government worker. He doesn't have a strong ethic. He does exactly what he's hired to do. He does not make anyone do anything and will not do anything extra. So when sodium moves in, we get something called depolarization. All right, so sodium is in the cell with potassium, and we get depolarization. So depolarization is an actual heartbeat. It's that moment, if it's a brain cell, it's that moment you go, oh, I just got it. I understand what 2 + 2 is for, right? Or it could be muscle movement. It could be the contraction of your leg as you're walking. When potassium moves out, we get repolarization or deactivation or cessation of depolarization. And we need that to happen because if repolarization continues, the cell runs out of energy. And depending on the cell, it could die and may not come back. And so think about your seizure patients. These are your patients that you may be seeing this with. And guess what happens? Calcium gets stuck at the door. Just like a restaurant, when you go to open the door to let sodium in, well, sodium comes rushing in, but then potassium comes rushing out, and they're stuck at the door. So let's look at how this works. We have calcium goes to the door. Oh, there it goes. Sodium comes rushing in. All right, and so when this happens, this is called depolarization. Right? This is when whatever function the cell has, it happens now. Now we're going to have potassium coming out of the cell. All right. When potassium moves out, we get repolarization or the deactivation, or when it stops, of depolarization. And we need this to happen so that everything can reset. So this is what it looks like right now. The school bus driver goes away. Calcium starts coming out because why? Nobody's looking. And so sodium's like, I'm coming back outside. And when sodium comes back outside, potassium's going to go back in. Once the majority of the potassium is inside the cell, the school bus driver needs to come to the school and tell sodium to move into the schoolhouse, and then tell potassium to come out of the schoolhouse. I hope that makes sense. And that's your electrical impulse. All right, so I hope that makes sense. I hope it helps. Maybe it does. That's going to be all for this video lecture, for first lecture. So you guys study up hard. Get ready for the next lecture. It'll be coming really soon. Have a great rest of your day or night. Hope you're either waking up or going to bed. See you soon.